what I'm going to present today is pretty much not only the challenges, but I'm trying to introduce some of the research areas that I'm focusing on to address that. So just to start, I guess it's a little bit about myself. I'm an underground geotech engineer. I've spent just over 30 years working in caving and caving projects and so on. Started my career with De Beers and then moved to Australia to help build the first block cave, which I'm quite proud to say I participated in that along with some of the colleagues online. And I worked at Rio for probably, I think it was just over about 22 years. And then I went and set up my own consulting, only because I was missing out on all the good technical stuff. So I wanted to get back into that. I think I've been involved most of my career in caving mines, mostly caving, certainly mostly underground. And I guess I sit on a few review boards. I get to see a lot of the caves, and I'm fortunate to have been involved in most of them, many of them. I've got a few papers out on caving, and I guess my claim to fame is with Rob. We introduced the whole hydraulic fracturing in cave mining back in '97. And then, yeah, somehow ended up joining the UQ with the W.H. Bryan Mining Geology Research Centre at the UQ. And that's really, they established this BLC, I beg your pardon, the Deep Mining Geosciences group, which they've asked me to lead. So just a little bit about that. So the Deep Mining Geosciences group is really part of the Sustainable Minerals Institute at the University of Queensland. So probably many of you have heard of SMI. And we pretty much set up this group because we were tasked to really look at setting up an industry collaborative type program of mining applied research that's really focused on deep mass mining. And of course, it's not just research, because as you all appreciate, education and professional development is a big part of that. So if you want to know more, then please, just look it up on the website or use the QR code here, and you can find out more about what we're doing. So just in case I don't get to cover everything, I just wanted to show you that there's pretty much 5 research pillars that we focused on. And of course, training is inevitable and a huge component of all of that. So I've sort of had that as the 6th pillar to the work that I'm doing. The first is around, I've called it geoscience characterization, because it's more than just geotechnical engineering. It's geology and it's hydro and it's all of that. And that's probably the most widely I guess, one of the largest concerns, the biggest concerns industry has as we're going deeper and we're facing cave mines, but I'll get into that later. The other ones are obviously around deep mining risks, rock mass conditioning. Note that I'm not calling it preconditioning, because it's both pre and post and during. My hobby horse, cave flow mechanics. We're also looking at alternative mining methods, or improving existing mining methods so that we better handle deep mass mining. And then, as I said, of course, training is a big component, which I really enjoy. So yeah, just a little bit of context first. Now, you might get a sense of my frustrations with on some of these topics because of the images I've got, but forgive me for that. It's the only time I get to show these. But really, my main point here is, as we're going deeper, we can't keep on doing the same thing, and we can't expect this sort of cut and paste approach that we've commonly seen, particularly in cave mines, to still bear the same fruit as we go deeper. And so I just want to talk a little bit about that. Why are we going deeper? Why are we focusing on deep cave mining, deep mining? Well, the fact of the matter is, there's this huge, as we know, there's this big push to go transition from fossil fuels to electric and so on. So there's a lot of critical minerals, and copper's one of those. And if I just look at the copper analogy here, a lot of the big surface and near surface deposits are nearly completely exhausted. I mean, outside of things like Escondida, even Codelco is going underground, is completely underground. And really, it's not a matter of running out of copper. There is copper. There's lots of copper, but it's deep. We're talking about 2 to 3 Ks. And the question is, how do we tap into that copper? We're looking at uh, doubling our copper demand. It has doubled over the past couple of years or past decade. And I've read, whether it's correct or not, that we're looking at mining more copper in the next couple of decades that we've mined in history. So clearly, there's this drive for more copper. And as you guys all know, copper price is soaring. I think today it was around $5 US a pound. So there's clearly a need, and most of these large, massive deposits that we find in these deep ore bodies are pretty low grade. So it's just a simple economics. Deep is complicated. Deep underground needs a lot of capital, and the only way we can produce those types of tons is clearly with a mining method that can deliver large tons at low grades to make it economic. So why do we use cave mining? So I wanted to put up this cartoon. Some of the times we barrel into talking about caving without really explaining what it is. And what I've tried to show here is a bit of an animation showing the different stages of caving. And it's important that I break up the caving into stages, because each stage has its own set of complexities, its own set of problems. So we try to break it up to manageable stages, if you like. So the first stage that you need to understand is that what is this caving? Well, we need to undercut the ore body. So this purple little purple thing on the cave initiation stage up in the top here, that's sort of, let's just call that the undercut level. And that level needs to be completely undercut. And I'll talk about that a little bit more. But in order for this cave to start propagating, for this cave to start falling in on itself, it needs a sufficiently large area. And this is what we call the undercut. Then as we start producing from the cave and drawing, so in the bottom right, I've tried to show you an animation here with LHDs and so on, going and drawing out of these drawbells, which these sort of silo-looking things that tap into the cave above. And as we draw this cave, so the cave propagates upwards and the rock mass unravels and starts failing in on itself. So that's the cave propagation phase. And then eventually this cave breaks through to surface mostly, or if there's another cave above it, it'll break through into that old cave. And so that is the next stage. And then obviously as we continue to draw this cave, so the subsidence zone expands laterally on surface. Now it doesn't become this bottomless pit hole. It does sort of tend to stabilize, and it's typically of the order of a couple few hundred meters deep, but nevertheless, it is an expanding subsidence zone. And as we continue to draw, so the subsidence zone expands. So very simply, that's caving. And so why do we do caving? So look, really, as we mentioned already, it's a very cost-effective mining method. We use gravity and the stresses to break up the rock. We only blast the undercut, and after that, it's purely we're at the mercy of the natural forces. And the neat thing about caving is it's really easy to mechanize. So the production level down, we have automated LHDs, or even if they're not automated, but it's pretty regular geometry, regular layout, and it's quite easy to be able to produce fairly high tons out of these mines. The only downside, I guess, is obviously you need high capital costs up front to be able to establish and develop this intricate network of tunnels and draw points and drawbells. But once it's there, it actually allows us to produce a lot of tons at a fairly low operating cost. So it's also very probably really one of the safest mining methods. And ultimately, like I've already said, it's probably the best suited to extract low-grade, large deposits and in large quantities. and certainly it's probably the only mining method or underground mining method that we have in our arsenal that can really meet the demands of metal in the future. And that is to say, and I've got to say this, that's if everything goes well. And all my time working on caves, I don't think I have an example where it's gone textbook well. All of them have their issues and problems, and I think that what we're going to see is those problems and issues are going to be exacerbated as we go down deeper. I love to show this, thanks to Chuck Brennan, with this sort of isometric view of Freeport. And I just wanted to put it there because it gives you an indication of the scale of the mining, of caving and this network of caves. And if you look at this, and this was, Chuck put this out in 2012, and it says that, Freeport, Indonesia will be mining 300,000 tons a day. I mean, that's incredible. And the fact of the matter is, I know that just this last year they've exceeded that, and I know their caves have produced in excess of 120,000 tons a day just in the cave. So really, it's the only mining method that can produce these types of tonnages, and that's what we need. And I just also wanted to show you the extent of this. I mean, these are large caves with hundreds of kilometers of development required. So the capital investment is significant, and most of that's all up front, right? For our mining engineers, I thought a more simple diagram might suffice. So what I'm trying to show you here is where we've come from and where we're going. Now, as I said, I used to work in De Beers, and really the early caves were really around kimberlites or asbestos mines and so on, and they were near surface. So you're looking at quite near surface with lift heights of the order of hundreds to 200 meters. If there's a lot of documentation on that, not only in De Beers, but Henderson Mine and various ones in the US, as well as Codelco in Chile. But as we've, in the sort of mid 90s, we had the North Parks that were sort of breaking the mold, in that it was the first sort of really solid, competent hard rock cave that had a lift height of around 500 meters. And then if you look at the lift 2, that went down to 850 meters. Currently at Oyu Tolgoi, lift 1, we're down 1,300 meters, and I think that's very similar to Cadia. Palabora is down 1,600 meters with their second lift. So we're getting deeper, and the lift heights are getting bigger. But where are we going? And I'll put a question mark. I'm just saying this as an example, potentially resolution, which is still a project. But if you look at how deep it is, the Burj Khalifa, it is, the Burj Khalifa is just an example. We could put a few of those and the Empire State Building into these heights of these caves with, we're talking about 2 kilometers by 2 kilometers by 2 kilometers deep. So they're really incredibly massive super caves that have, quite different to what we started out with in the past. And the point I'm trying to make here is that the scale and the depth are unprecedented. And deep mining can be very unforgiving, and certainly there's not a lot of room for error there. Now, why do we go deep, you might ask? And I think it's pretty obvious. I've already said, we have these deep high column caves really for a simple reason, and that it costs a lot of money, a lot of capital up front to develop these mines. So you can imagine if we have a very high lift, we can reduce our capital spend. We rather spend it once than several times. So we see this transition from near surface shallow block heights to deep high column caves. And you've got to understand that all this capital investment, and if you look at what's out in the public domain, Oyu Tolgoi is in excess of 7 billion, and most of the others are, most caves are, you're talking billions to set up, and that's before you've even mined a ton of ore. So quite a lot of risk up front, and you want to be able to bring this cave into production as soon as possible, and you pretty much want it there for the next 10 years or so. And so really, it's a matter of the profitability being a function of the height, if in effect. yeah, to be able to meet these large tonnages and reduce capital spend, increase, I guess, reduce your operating expenses as well. We really want to go deeper and have these higher columns, but they do bring about more risk, and I'll talk about that now. So yeah, let's just talk about these deep high column caves. So first thing, excuse my cartoons, but what I'm trying to show here is that pretty much these shallow caves that we've had in the past were really low stress caves, large tensile zones, where tensile zones are a function of the span. And what you might argue is that a lot of the work that was done by people like Loebscher and so on to predict things like the caveability of the deposit were really based on near surface caves, right, where the stress regime is quite different. It's quite different to something that has a high column and deeper, and you've got to question how applicable or are these empirical criteria for these deep caves. Now, I'm a big fan of what Dennis Loebsch has done, and I'm not criticizing. I think he's really brought so much to the caving world. But we just got to be careful when we try and apply some of the empirical methods that were designed for a different, I guess, different environment and a different circumstance. We can certainly learn from them, but we just got to understand their limitations, right? So one of the big things with these caves is that we've got to realize that because they're deeper and because they have are really high columns with large aspect ratios, is that the ability to cave is not just, well, it's not just a question of caveability, it's a question of how these caves cave. So if you look at the examples I've just pulled out of publications, you can see that potentially there's quite a lot of ore at risks that we can't recover. Remember that we've only got draw points to draw to control the propagation of this cave, and then we're at the mercy of natural forces. So there is certainly a lot of precedent in our modern caves with these high aspect ratios for us to leave a lot of that resource behind. And that's a huge risk that we really need to address, and it can be addressed. I'm not saying it shouldn't be, but we must be aware of this. And certainly, I think that it's very important that our shareholders and investors understand this, because if we go there and say, well, we're going to recover everything at 100%, I don't think there's precedent anywhere in the industry yet that has done that. But anyway, it's a lot more challenging when we have these high aspect ratios. So I want to just talk about undercutting now, and I want to just say that it's one of those methods that's really important for block caves. The undercut level is a key, and the undercutting process is really key to sustaining the integrity or preserving the integrity of the rock mass on the production level. And we really need to be careful that we actually protect that rock mass. So what is an undercut? First of all, I think I've already mentioned this, but just quickly, look, it's when we cut out the slot or the stope down below so that we can get caving to naturally occur. So we cut out the slice near the ore body, we blast that out across the ore body, and then caving is induced. Now, just a little 2D section again for my mining engineer friends. Look, what we've got here is just a section through the undercut. We show the extraction level, the production level, and the undercut level. And here we've got the rings that we're blasting and we're retreating towards the right. Now, the thing is, with conventional undercutting, these drawbells we have here, which are these blue cones, if you like, silos that we're developing, if they had developed a head, that's what I'll get into that, but you can see that this is what we would call a post undercut. Now, there's different types of undercutting, but how we do it is important. What we want to do when we undercut is preserve the integrity of these drawbells and these pillars between the drawbells, because you've got to realize that these drawbells and draw points have got to draw, especially with high column caves, probably well in excess of 300,000 to 500,000 tons each. So, you can imagine a lot of wear, a lot of loading. And so if we're going to keep them in production over their life, we've got to really look after the integrity of that rock mass. So this is where we come to the different undercutting scenarios. So the more classic post undercut or conventional undercut, this is where what we have is what characterizes this type of undercut is that we have the drawbells and the pillars and so on, the draw points developed ahead of the advancing undercut face. So what you see here is the red line showing these very high abutment stresses that break up the rock, but you can see that they serve to sort of smash, if you like, or really load up the development that occurs ahead of that abutment face. So that's a unfortunately it's a bad side effect of this method. The good thing about this method, obviously, is that it does allow the miners to divorce, or if you like, separate the development of the extraction level and the undercut level. So you're not constrained in any way, and you can bring the cave on quicker. And we already said that that's a really nice feature. To be able to bring a cave on quicker is really good, because it allows us to get production in earlier. The alternative to this is that we use what we call an advanced undercut, where the undercut exceeds or is in advance of the development. Now, the nice thing about this is you can see that the high abutment stresses don't break up the draw points and the drawbells. And that's great, because it sort of preserves the integrity of that, keeps it, if you like, alive for longer. And it's a very effective method of de-stressing the rock mass that we want to minimize damage in. So it really is good for that. The problem with this undercut, though, is that it does constrain the advance of that undercut. So you can imagine the logistics. That undercut rate in advance is really constrained by the development of the draw points and the drawbells. So it is a balancing act. It's very important that this is synchronized, and this does slow down the undercutting process. And that means that a cave with an advanced undercut comes online slightly later than, say, if you adopted a post undercut. But there are problems, right? So you can imagine, especially when you have a lot of high stresses, what we find when we undercut, we get a lot of drill and blast holes, on the undercut. We get a whole lot of hole dislocations. We get incomplete blasting associated with that. And so what we do is, what we have is we can get these pillars forming in the undercut, which I'm trying to show here. And these pillars become stress concentration. And that's a real problem, because down on the production level below, all the stresses tend to focus and concentrate on that, then we point load, I guess, the tunnels below. This tunnel over here, you can see this was a 5x5 or 6x5 meter tunnel that's completely closed. Why? Because we left a pillar up in the undercut. So this just shows you how extensive the damage is. What I'm showing you here is hot off the press. I won't tell you where it's from, but if you look at this tunnel, we're flying down a production level. Look at the damage that's caused. Now, this wasn't a rock burst. This is purely from a pillar left on the undercut. Now, I won't tell you where, but the point is the damage is extensive. And imagine this is what you're doing. This is the type of damage that you can get if you get an incomplete undercut. You can completely obliterate or severely damage the production level below, because of the incredibly high stresses above. And this is the type of thing that we've got to minimize, and we can't afford to leave these pillars behind. The problem is, though, the higher the stresses, the more difficult the drill and blast process is. So I won't keep going, but the other thing that we've got to realize, I just showed you a problem, if you like, with static stress problems, but we've still got the dynamic problems. And here we have rock bursting that occurs in cave. And this is not uncommon, where we have pretty hard rock and we've got these very high abutment stresses, and they can produce rock bursts. And they're not pleasant. What is a rock burst? It's pretty much a violent ejection of rock that typically explodes outwards. And I think it's best if I just show you some videos. If you look at these videos, hopefully you can see it. Watch the wall on the right, and you can see what a rock burst looks like. There you go. Now, just want to point out, both of those guys were okay. They might have had to change the underpants, but nobody was hurt here. So it just gives you an example of what an undercut looks like. Here's another one. Now you'll see the burst occurring from below in the footwall. Watch that LHD. Watch this jumbo be ejected upwards. And you just think that's a couple of tons of jumbo being pushed up into the air through a seismic event down in the footwall. So it's pretty impressive. The energies here are incredible. Now, what I'm saying is that we need to do everything we can to minimize this type of damage and exposure to personnel and so on. And the way we do this is sensibly undercutting. Now, just as part of what we're doing in this space, I just want to plug for the DMG. We're looking at undercutting methods. We're taking data from some of our mines, and thank you for those mines that have sponsored this. Particularly want to shout out to Oya Tallboy, who has the most extensive extraction level monitoring I've ever seen and has ever existed. But that really allows us to look at that. And we've got a master student here that's done a lot of excellent work, especially back analyzing all of this and looking at the type of deformations that we're seeing. And that allows us to compare the undercutting methods. Now, we're not comparing models. This is actually real data. So we're comparing undercutting strategies, and we're looking at the deformations that we're getting on the extraction levels. And we're trying to evaluate and demonstrate quantitatively, exactly what this is, what types of undercuts are best for deep caves. And from that, we hope to come up with some suggestions, modifications, and perhaps looking at ways of improving the undercut method. We're also looking at things like rock bursting and being able to quantify the pros and cons of the different methods and the risks that are associated with these methods. And really the idea is to be able to develop a reliable, suitable mining undercut level for these deep environments. I'm not going to talk too much about rock mass preconditioning because I have a bit of a section later on, but obviously one potential way of managing high stress and rock burst potentially is through rock mass preconditioning using hydraulic fracturing. But this is what we're doing currently, and anybody has data, thanks for those who have provided, North Parks, Freeport, we really appreciate your support. The other thing, by the way, I thought I should just throw it in here, we're also looking at geohazard management, and so we're doing some work to be able to use data, not models, use real data, doing back analysis of this data, linking it in with the production and the undercutting, and looking at how we might be able to use machine learning methods, so data-driven applications to better design, better manage these geohazards. So we're looking at developing more real-time type geohazard or georisk tools that could, I guess, using machine learning can be more predictive and give us a bit of a warning about potential hazards occurring ahead of undercutting. I'm not going to elaborate on that too much because I haven't got time, but for those of you who might be interested, I'd love to talk to you later. So now I get to talk about my bugbear, which is really talking about cave flow mechanics. The key terms here are interactive draw, and that's really important to be able to manage cave loads and dilution ingress. So really important. I think it's probably one of the most important topics that we're researching. So the challenge, just for you people who don't understand or don't appreciate this, is that I guess the issue is you can think of these all the draw points, draw spacing as these big silos that we develop, and as we draw from these draw points, so we develop these cones of movement. Now, theoretically, what we're trying to do is get the material that's moving in the cave to I guess move as a mass flow. So what we're trying to do is get it all moving uniformly, and the only way we can do that is to design our caves to be correctly spaced. In other words, all the draw points need to be near enough so that they can facilitate this mass flow and this interactive draw. But at the same time, we've got a delicate balance between interaction and stability of the extraction level. We can't have the pillars and these silos or these drawbells too close, so otherwise we cause instability in the pillars. So there's this tension between stability and interactive draw. But the consequences of this lack of interaction, which we call isolated draw, is that we get a lot of problems associated with that, and I'll talk about that in the next few slides. So excuse my cartoons, but on the left, what I'm trying to show is the difference between interactive draw and isolated draw. So if you can assume that this brown-looking red rock is waste, then if we have no interaction between, with these ellipsoids, then what we get is, if you like, a bit of a dead ground between these ellipsoids. And what that means is that the draw cones are narrower, and consequently the rock that moves down into these draw points moves a lot faster. And so if you've got waste material sitting above you, what that means is it enters your draw points a whole lot quicker. The other important thing to note, though, is you can imagine what I've got on the right here is just showing this is a particle flow code model that was developed many years ago, over 20 years ago now. But what it shows quite nicely is these thick black lines are essentially forces, contact forces between the particles, the balls. And where you see thick black lines, basically that means that's where the stresses are concentrating. That's where the forces are highest. What this shows is that if you're getting a lack of interaction between these free-flowing cones, basically the stresses can, if you like, concentrate between them. And that's not good, because that means the stresses can push through them. And what are these stresses? Well, it's the kilometer of dead weight you've got above you, right? Interactive draw, on the other hand, as this right-hand diagram shows, is that if you've got material that flows and interacts, the stresses can't build up in that material as easily because you keep on moving it. It keeps on flowing. Stresses don't have time to build up. Now, what does that mean in reality? Well, it means that if we've got these stresses that sort of are channeled into these areas that aren't interacting, then we can have enough of the stresses to punch through down below and close draw points, as I'm showing you down here. This was a tunnel on the bottom. It's completely collapsed because of the loads above. We get these point loads forming. The other problem, so here's just an example of point loads, I guess, from pillars left behind or crushed pillars, things not interacting. And here again, so it cuts across the industry. There's very few mines that don't have crushing out of their draw points because of weak rock and pillars that have been left behind. The other thing is, and what I'm trying to show with this cartoon, this was done many years ago thanks to some students that worked for Rio at the time. But basically what we're trying to show is just to use a very simplified cellular automata here. And it's based on real data. And what this is showing is that if you have, in this case, 3 draw points that are being drawn, if these cones, the material that's moving is fairly narrow, as I've shown here, if you have these draw cone ellipsoids with only an 8-meter diameter versus one with a 13-meter diameter, clearly you can see the 8-meter diameter material moves down a lot faster. Now, if that red-brown material is waste, what that means is you bring it in a whole lot quicker. Now, when I showed the first slide, beg your pardon, that black thing is supposed to represent a loader tire. So in my past life, I used to put a whole bunch of LHD tires on levels above to see when they come down. And much to the disgust of the maintenance manager who had one of these things stuck in the crusher. But look, the point is that we wanted to try and get an understanding of how quickly the material flows down into the draw points and how it flows. We've got a lot more, we've got excellent data nowadays, cave trackers, smart markers that are a lot more better at looking at this than an old loader tire. But the point is that when you have isolated draw, if you can see, my loader tire got to a draw point in just 12 months where draw was narrow versus 33 months when it was wider. So that's real data with a cartoon to illustrate. My point is that if we don't get interaction, we get a whole lot of dilution really quickly. And there has been a lot of precedent of that. Not to make, I know there's published by Parks. Thanks for Parks for allowing me to publish, to show this from their publication. But this is just when they had clay in the E26 Lift 2. I see Sarah's online. I'm sure she can tell you a lot more about that. But these are really real problems. If we don't want this type of, I mean, we're a copper mine, not a pottery class. I mean, we don't need this type of thing happening early, because in effect we sterilize ore. So it's really an important problem. How else can we see this manifest? Well, if you just look at open pits, you see these what we call rat holes forming. If you start seeing this type of thing on surface, you know that interactive draw was never happening on your mine. So I guess there's a lot of issues with that. Now, I can imagine, why do I care if I have these little rat holes forming on surface? Well, if you in an area that has torrential monsoonal rain, and now you've got these conduits down onto your extraction or production level below, you can imagine that there's a lot of water that becomes channeled down here, and that could be quite catastrophic from a mud risk point of view. So not nice. What we're trying to achieve in caves is interactive mass flow, not isolated draw. With that said, I guess one of the biggest projects, and thanks to those sponsors here, is that we're looking at interactive draw and mass flow and isolated draw using real data. So we're looking at cave trackers, smart markers, any markers, and as well as draw point observations. So we're looking at the grades from the draw point, what type of geology is coming through, all of this type of data that we're integrating and we're linking with the production tonnages. And the reason we do that is you can't, it's cause effect. We've got to look at how this mine was drawn versus what we're seeing. And from the data, we're able to, looking at it and looking at the different flow mechanisms that are predominating. And it's a woeful tale, to be honest, because almost all the mines that we've been looking at are showing some form of isolated draw, if not predominated by isolated draw. So it's very important, because we're trying to achieve interactive mass flow, and we really need this, because we there's a lot at stake. We've developed these mines deep. We have these huge high columns, and we need these mines to stay operational for their life. So we can't afford to be diluting them or to crush them, because we aren't able to dissipate stress and so on. So interactive draw, really important. The data has been remarkable in that it's really showing, well, it's really showing what we really know, but we are looking at what how we might be able to draw caves and sequence them, sequence the draw to try and minimize the isolated draw effects and try and get more interactive draw occurring. And I guess there's a lot of work to be done. At the end of the day, what we're also trying to develop is more of a real-time monitoring tool that can take our data as well as our production data and look at it in real time and sort of inform us as to whether we're getting isolated draw, where we're getting it, and how we might be able to manage it. It's a difficult task, but we're getting some. We are having some success with that. So I'm quite pleased, and I'm pretty sure as we can use more of the machine learning and AI technologies, will be even better and faster to be able to predict how the material's flowing. I guess one of the things that this is also pointing to is that we're going to come up with another way of designing our layouts underground, because once we've built these caves, we really don't have the flexibility to change. Yeah, so I'm not going to talk too much about this, but obviously one of the biggest concerns we have is our inability to predict the rock mass response, especially in caves. And I've got to say that since I've left Rio and had more exposure to other mines and have reviewed other mines, other caves, I'm pretty disappointed by the amount and the quality and the quantity of geotech data that's collected. Frankly, we cannot develop reliable geotechnical models with token data. I mean, it's not an afterthought. Right from the exploration phase, we need to be thinking about geotechnical data collection, not thinking about it. We need to be collecting it. So, and a lot of it and good quality. And when I say that, I mean, we need to develop this reliable geotech model. because this is the basis of all our predictions, all our modeling, and so on. So we can have the fanciest 3D model, but if the data behind it is suspect, then we've got no chance of being able to do any predictions. So we really need to be more confident and do better in the space. And to that end, I just want to show this. Some of the mines, many mines, I'm coming across at best have RQD data only or initially, and people say, well, at least we collected that. Well, I wish you hadn't actually, because it's telling me nothing. And I just want to point out, RQD is very vulnerable to the orientation. It suffers from an orientation bias. What I'm showing by this little diagram here on the right, thanks to Jarek Jakubek, is that it just shows that RQD, if you have RQD can vary depending on the orientation of your drill hole. It's a very poor index of rock quality. And if you look here on the right, I'm just showing you some core trays. All of these 3 trays have RQD of 0, but I'm pretty sure you're not going to design your tunnel to go through the top one, right? You'd much rather design it for the bottom one. So unfortunately, if all you've got is RQD, you have no idea. So I just wanted to point out that quality data is absolutely imperative if we're going to do justice to predicting rock mass responses. Now, to this end, what we're doing in this space, it is a project that I must say has been struggling to get going. But what we have found is there's so much data that is collected outside of just geotech logging that isn't being used. And so I've got this project called Data Fusion. And what we're trying to do is take all of the data sources that we have, merge them, integrate them. I could have said data integration, but it's just not as sexy as Data Fusion. So Data Fusion, bring all the data together and let's have a look at what it's telling us. So we're talking about not only the geotech core logging, but the geology logging, but especially the downhole geophysical data, the ATVs, the full wave sonics, the multi-channel sonics, the hyperspectral logging. There's a lot of information that we really don't do justice with. So what we're trying to do is integrate this data together so that we can start looking at where we lack data in one area. We might be able to fill it up with gaps from another, and use this to form a more reliable model. And it really does, I guess, help plug the need, especially when we have sparse data or we have poor data. This really will help. And so this project, I think, is really an important project. We're making some headway. There's a lot of really novel scanner data out there, but we still lack the integrating that data into one, if you like, database. And I think that's where we're going in the future. And I do believe that from that we can again use things like data-driven algorithms to better analyze the data and come up with better rock mass properties and so on, so that we can build better models. I'm not doing this much justice, but I think you get the point in the picture that integration of geodata has got to be something we do. We can't afford to drill 3 holes and try and build a geotechnical model out of it, or collect RQD only and expect miracles. We've really got to start using all of the data. I know that people want to drill less. Well, the only way we're going to drill less is if we integrate all of our data and then we start right from an exploration phase. Just a quick topic on rock mass preconditioning. Why do we do it? Now, what I've talked about here, it's really around hydraulic fracturing, and I've called it rock conditioning rather than preconditioning. But what we're trying to do is really weaken, if you like, the rock mass, change the modulus, lower the stresses, and all this type of thing by injecting fluids into the rock. Now, I've been doing this for a long time, back in '97, and unfortunately, we have come quite a long way as far as improving the technologies to do it. We don't drive a dirty, great big diesel truck underground like I used to do. It's now all electric and so on. But as far as understanding the mechanics behind the hydraulic fracturing and what works and how it's influencing the rock mass, we haven't really made any inroads there. That is not sort of empirical or qualitative. And what we really want to do is we want to be able to understand from a caving point of view is what we're doing to that rock mass when we inject hydraulic fractures into it. How are we breaking it? How are we changing its character? How are we effectively reducing the rock mass strength? Are we changing the stresses? And everybody says yes, because we've done it everywhere. But most of the work that has been done is rather observational or qualitative. And I can say from personal experience that I have also managed in the past to elevate the stresses considerably by injecting hydraulic fractures into a high stress rock mass and putting in proppants. So I thought I was going to help reduce the modulus, but all I really did was raise the stresses. So best we know what we're doing in this space, because otherwise we can make a bad thing worse rather than better because of our ignorance. So I think that in this space, again, in the DMG space, we're looking at a lot of work analyzing hydraulic fracturing monitoring, and we basically, again, using more back analysis of mines. We've been doing this now for over 20 years, or around 20 years, over 20 years, and we're looking at trying to get the mines to collaborate here and give us this data and improve our understanding of hydraulic fracturing to be able to modify these mechanisms. And the other important reason for this, by the way, is that we sort of think we can just simply apply it as we go deeper. But some of the hot dry rock projects that were completed in the turn, 30 years ago, certainly in EU and so on, there's a lot of precedent that we cannot create horizontal hydraulic fractures in deep rock masses, and all we get is this downward migration or shearing of these fractures instead of opening mode. Now, that's quite important to understand the mechanics at deep, because what that means is that hydraulic fracturing as some sort of tool to de-stress rock masses at depth could just be just ineffective. And part of the reason is how hydraulic fractures form in deep at depth, I guess, is quite important. And I don't believe that we truly understand that. I think there's a lot of ground to be covered and a lot of work to be done to understand how stress, temperature, and so on affects the effectiveness of hydraulic fracturing as a preconditioning or hazard reduction method. Now, I guess finally, I just want to talk a little bit about the professional development training. I think we all know that we're in a bit of dire straits in the mining industry. There's the so-called gray tsunami happening in the US, where more than 50% of their workforce is going to be retiring in the next 10 years, or by the end of this decade, and that's pretty serious. And also, this is sort of amplified by the fact that we just don't have many mining engineer students coming through, or mining students at all. We're finding that a lot of the schools are closing. From an undergraduate point of view, we're in a bit of strife. We're not turning out engineers, and to be honest, in many cases, the engineers we are turning out have to cover such a wide content and syllabus that they're not necessarily digging deep into some of the content because they have to cover so much. So I guess where this is leading to is that we have a pretty significant skills shortage that we're concerned about in the industry. And I've been doing professional development training, particularly for professionals that aren't familiar with caving, mostly caving and underground geotech focus. And it's just amazing how well that's gone. I haven't had anybody come to me and tell me that was a waste of time. I think most people have got a lot out of it. But it just shows that there's a desperate need to be able to train up our professionals, but as well to sort of bridge the gap between our graduates and the professionals we need. So it's not only a matter of upskilling them, but also giving them that practical experience as well. That's more and more lacking in our minds today. So I guess there's with that, just so you know, we've got a lot of professional development courses. I certainly do quite a few. Watch this space. We're about to put an announcement out in the next few weeks, I think, where we hope to really do a lot more in the space. So for those of you interested in more professional development, particularly underground geotech or caving, please keep us in mind, because this is going to be a fantastic opportunity to be part of that. And a lot of what we're doing is very hands-on. It's very practical. So we're trying to address the real need in industry, not just give theory. So and to that end, I'd also say that if you've got people wanting to do PhDs or masters, and especially around the caving or underground geotech or deep, then and you see any of these research projects that I'm putting out there, if you're interested, let me know. We'd love to be part of your training program. So yeah, look, I really screamed through that. Apologies for going so quick. I have left a few minutes for questions, so I might just read some of those online. So Kim sent, could I use a mixture of post or advanced undercutting? It's not that simple, because really you've literally divorced the two. So in effect, if your question is, can I develop some things ahead of the undercut and not everything below? Well, that's what we do to try and speed up and improve the schedule. So you'll see most mines have all the extraction drives already through. Some of them even do the draw point stubs. But I think really it depends on your mine and your rock mass response as to what you can get away with. My thought is that the deeper we go, the less we're going to be able to develop upfront. No doubt we always need to develop the drives, not only from a rock mechanics point of view, but a practical point of view, construction point of view, but it's also a ventilation issue, right? So from that point, you can have this mix. But really, when you're talking about advanced undercutting versus post undercutting, I'm predominantly talking about the drawbell development, because that's where you cut a lot of the rock out. And that really weakens that ground ahead of you. And then if you've got the undercut going over the top of that, you really do a lot of damage, potentially anyway. Sam asked, has DMG being involved starting any research on wet muck hazards? Is there a way to estimate? Yeah, well, look, my rat holes in the open pit, is there a way of estimating or forecasting those rat holes? Yeah, well, yes, there is. Well, sort of. I guess first question, the wet muck is very closely related to isolated draw, and a good colleague of mine, Gert van Hout, has done quite a bit of work in that space, and maybe he can share, I'm not sure, but there's a close link between isolated draw and wet muck and how we're drawing it. So there is, I think there's a whole lot of consequences of isolated draw, and certainly this does feed into that. So it hasn't been a focus per se, rather an outcome of the work that we've done. So Stefan, to get horizontal hydraulic fractures, wouldn't you need the 53 principal stresses to be vertical? I beg your pardon, S3 principal stress to be vertical. Yeah, better than 53, just S3 is a lot better. Look, yes, you're right. I guess the problem is, as we're going down, we probably have a more of an isotropic type stress environment, don't we? So we're going from obviously we're transitioning from a predominantly high sub-horizontal sigma 1 or low sigma 3, but then, as we go down, that flipping of sigma 3 with sigma 2 can be the problem. So it means that you can easily go from horizontal to vertical quite simply, because it's, all you need is a fluctuation between sigma 3 and sigma 2, right? So I think but it is an issue. It really is. Alan, how often is geological structure and domains considered incorporated in flow models? Seems like shown models are assuming a very homogeneous. No, absolutely not. There's no rock mass that's homogeneous in caving, and geological structures are absolutely key, and they're domains in themselves. And a lot of the flow work we're showing is that, well, a lot of the isolated flow and isolated draw we're seeing in our data is associated with large fault zones and shear zones. So it certainly didn't mean to show or imply that our rock masses are homogeneous. They're far from it. They're very, very heterogeneous, and they also have a lot of structure, especially porphyries. Jasper, have you ever been advances or studies through deep caving with major hydrological factors at play? Um, watch that space. I personally haven't. I think the one mine that the cave that comes to mind that probably has the most experience with a lot of water is probably Freeport. I don't think anybody has as much Freeport, Indonesia. So I would suggest you talk to those people. I know Jeff Beal has been doing a lot of work in the space, so maybe contact Jeff Beal. But certainly, you know, I'm not sure what the links are necessarily with deep and hydro. I haven't made that connection yet. But there is a lot of issues with hot water in a lot of new mines, and let's put it that way. And I think that's a topic that we need to tackle very quickly. Can you comment on how bridging occurs in a cave, and have you led? Yeah, so bridging, you mean if the cave's hung up? Yes, we've been involved in many a cave hang up. I would point you to Massman 2000 paper I wrote when I used hydraulic fracturing to help induce caving at North Parks. Certainly the North Parks E26 Lift 1 is a case in point. Rock bridging, a lot of people, it's happening in a lot of mines. They're just not as forthcoming with their information. It's not topical to publish your dirty laundry out, right? But you just have to look at some of the publications, and you can clearly see they've had problems just from the diagrams that they put in their papers. But if you want to talk about bridging, how you overcome that, yeah, look, there's quite a bit in the literature. Any insights for predicting fragmentation using empirical versus numerical? Yeah, look, I've done a lot of fragmentation, cave fragmentation predictions. We typically use block cave fragmentation or BCF. There's some things you need to know when you use it. I think, look, it is always empirical to some point, but what I'm telling mines more and more is it really depends on how good your data is. So in terms of numerical, if you just mean put it in a black model or something, no. I mean, I think you need to do a specific fragmentation analysis. There are tools, but really, like any modeling, it's only as good as the data you collect. So if you've only got RQD data, then good luck to you. You've got no chance. Any insights, big one? Hannah, in regards to chimney rat holes, do you have any indication on how isolated draw compares to geological factors? Yeah, like I said, major structures are pretty key. Weak domains and so on are key. But I've got to say, by far, I think the way you draw the cave and the rates of draw are major, as well as the fact that we're designing our caves so wide, so far apart. Our draw point spacings are excessive, and to be honest, they over excessive. So I really do think that's the only way we're going to manage some of these the interaction problems is to bring our draw point spacing in. Yes, I know people think that's a stability problem, but I think if you look at the collapses we're seeing, it's not pillar collapses, it's drive collapses. If we really want to deal with the problem of instability, make your tunnel smaller, and then you'll have far better stability on the level, rather than make your tunnels as big as you can, and then you have these massive spans, and you attribute all this failure to pillar failure, and it's not. It's purely spans. The spans are so wide they can't sustain the rock mass can't sustain it, and so we're getting collapses. If we really want to sort this out, bring in your draw point spacings and reduce your drive sizes. Yeah, sorry. I'll wrap up now. I've only just seen that. So anyway, pretty good timing. It's 3 o'clock. Thanks again for everybody who joined in. I hope you got something out of it. Please feel free to email me. I'm more than happy to answer emails as best I can. You might get a delayed reply, but I'm always up for replying to the emails as best I can. So thanks everybody. I really appreciate you joining in.